let's reconvene for the third lecture by Professor Black. And then, yeah, please.
Right. Okay, let me resume from where I was the last time. I want to continue with a very brief introduction to radiative transfer in astrochemistry, how to relate the spectrum that we can observe here on Earth to the physical conditions in the source region somewhere in space. And then I wanted to just discuss a couple of case studies that are of special interest to me recently. Okay, now I had shown this one previously. This is just the absorption cross-sections for two molecules, hydrogen and carbon monoxide, as a function of wavelength in the far ultraviolet. And this is important for understanding how both H2 and carbon monoxide are associated by ultraviolet starlight. And the blue curves show the wavelength dependence of the cross-section in these spectrum lines. These are electronic transitions with vibrational and rotational fine structure. The blue is the hydrogen. Again, I've also stuck in the Lyman lines of atomic hydrogen. And the red is the carbon monoxide. Now, for the molecular hydrogen, you're seeing individual lines. In the case of the carbon monoxide, this is an entire blend. It's a blend of an entire electronic vibrational band with rotational fine structure. But that rotational fine structure is all washed out, except for hints of the P and R branches. And in addition, this CO band has very extended line wings, and that's the signature of a very strong predissociation in the upper state of the transition. So to do these radiative transfer calculations accurately, one actually has to take into account all of these details, not only the rotational fine structure in the transition, but also the upper state lifetimes, because that affects the propagation of the radiation in the wings. And even though this is a logarithmic scale, logarithm of the cross-section in megaparts, that it turns out in practice, if we're trying to model the penetration of ultraviolet starlight through a column of H2 and carbon monoxide near the peaks in these cross-sections, the absorption rapidly with increasing depth, the absorption becomes highly saturated, so that in fact, within a relatively thin column of molecules, the dominant absorption is actually taking place in the extended line wings. So one has to treat that. So this is just to give an idea of what we need to think about in putting an absorption cross-section into the radiative transfer equation. And then let me illustrate with the concept of a simple, pure absorption spectrum, no scattering of light, no angle-dependent scattering, simply an absorbing column of gas. And you've seen an equation like this before in reference to laboratory absorption spectrum. It's basically the same idea. Here's an example of an actual astronomical absorption spectrum, again in the far ultraviolet. And this piece of spectrum, this is a very small wavelength interval, this piece of spectrum is completely dominated by lines of molecular hydrogen arising in different rotational levels. And you see in the central part here, where we actually have a blend of what looks like a blend of lines arising in J equals 0 and J equals 1. And in J equals 1 here again, that these absorptions are so strong that they go all the way to 0. And it's actually a testimony to the marvelous optical design of the Space Telescope imaging spectrograph, that the scattered light, the instrumental scattered light, is essentially negligible, that these spectra can be accurately calibrated so that they do actually go to 0 in the highly saturated regions. Okay, this is actually what we see analyzing an astronomical spectrum, but this also gives us an insight into what the hydrogen molecules in that diffuse molecular cloud are seeing. And in particular, the hydrogen molecules in the center of this cloud are seeing 0 ultraviolet photons in this wavelength interval. Okay? And so that's actually the way that hydrogen molecules shield themselves against ultraviolet photons. So but H2 and carbon monoxide and the nitrogen molecule are very, very special, because those are basically the only common species that have line photoabsorption that leads to the dominant dissociation process. It's much easier for almost all other simple molecules because their photodissociation is accomplished by continuous absorption processes. Okay. Yeah, I think that's all I need to say about that. But let me talk with reference to adiabatic potential energy curves. Fortunately, I have an audience of chemists, so I don't have to explain what those mean. But we can describe the electronic states of a simple molecule like H2 in terms of these potential energy curves, potential energy versus internuclear distance. And because, as you know, the central part of a typical diatomic potential energy curve like this looks very much parabolic, that is like the potential energy of a classical harmonic oscillator, only turning slightly anharmonic at larger distances, that we can sketch in the energies of the bound vibrational states. There are 15 of those, labeled V equals 0 to 14, in the ground electronic state of H2. This shows the energies, 4.5 electron volts approximately, energy difference between the ground state and the dissociation limit, the asymptote of the potential curve that tends toward 2 ground state hydrogen atoms. There is an excited state that goes toward 1 ground state atom and an N equals 2 hydrogen atom, and in particular it's this state that forms the upper states that were involved in that last spectrum, piece of spectrum that I showed. With the red arrows here, I want to illustrate what happens to a hydrogen molecule in space exposed to at least some of the ultraviolet starlight. Most of the hydrogen molecules, most of the time, are in the lowest state of vibration, but they may have some distribution among rotational fine structure levels within that. So from V equals 0 in the ground state, an ultraviolet photon is absorbed, excites the molecule into some distribution of excited vibration rotation levels. The rotational quantum number can change only by 0, but there can be a broad distribution of final vibrational states here following the absorption. And then there are two things that can happen. After pondering the matter for about a nanosecond, the excited molecule then will decide to undergo a spontaneous transition back downwards. And that can go to one of two electronic states. Some of the fluorescence downward goes into a repulsive state that also correlates with ground state hydrogen atoms. But that supports no bound levels and is energy above the dissociation limit. So that's the process, a two-step process that leads to the destruction of the hydrogen molecule, liberating two hydrogen atoms with some excess kinetic energy that is actually a source of heating as those kinetic motions become thermalized later on. Averaged over all of the electronic transitions of H2 and weighted by the spectral shape of the starlight, that channel occurs approximately 10 to 15% of the time. The other 85 to 90% of the decays go to a variety of possible mostly excited vibration rotation levels in the ground electronic state. So the molecule is preserved, but it's excited. And there follows a cascade of radiative transitions. However, as has been mentioned several times, the hydrogen molecule is a completely symmetric structure. The center of mass, center of charge coincide, so there is no permanent dipole moment. So these radiative transitions between vibration rotation levels of the ground state can occur only as electric quadrupole transitions. So let's put numbers on the transition probabilities. The transition probability for this particular transition, where we looked first at the upward absorption, that A value is about 3.5 times 10 to the 7th per second. So that's very rapid. A strongly allowed electronic transition involving two different electronic states. But in order for this rotation vibration cascade to relax back down to the ground state in the interstellar medium, we have to consider the transition probabilities here. And for a typical delta V equals 1 quadrupole transition in H2, this is now 14 orders of magnitude slower, 3.5 times 10 to the minus 7 per second of vibration rotation transition, and even slower still for a pure rotational transition as an electric quadrupole. This one from J equals 3 to J equals 1 goes at about 5 times 10 to the minus 10 per second. Now, by laboratory standards, those are very slow rates, of course. But in the interstellar medium, in fact, these are fast enough that typically a hydrogen molecule in a low-density diffuse molecular cloud has plenty of time to radiate several steps in these very slow transitions and get itself back down, at least to the ground vibrational state. Okay, so again, all of that has to be taken into account if we're going to, in particular, if we're going to try to calculate in a model the fraction of these UV absorptions that lead to dissociation, the fraction that produce excited molecules, and then integrate that over path length through the model cloud, taking into account how the absorptions closest to the resonance get wiped out, leaving no UV photons deeper in the cloud, so that all of the continuing absorption takes place far out to the wings of the UV absorption line, with much reduced probability. Okay, so that's in words, that's the problem of coupling the radiative transfer to the excitation of the molecule, which in turn affects how rapidly it undergoes inelastic collisions with other hydrogen molecules, and on and on. So all of these things need to be taken into account simultaneously. Through the ultraviolet observations, we can observe directly the populations, again, the number density and rotational level J of the ground state per substate, a logarithmic scale versus excitation energy. And it's one of these situations that Tyson showed one in the previous talk, that on a graph like this, the Boltzmann distribution would appear as two straight lines. And so approximately speaking, there seem to be two straight lines on this excitation diagram. And notice that it extends all the way up to 2500 Kelvin. Right. The open circles are observed values, blue circles are model values. This is not one of my models, but one can discuss why the model doesn't fit perfectly, but it seems to get the slopes right in any case. As it turns out in the model, the way that H2 behaves in the diffuse interstellar medium where it's exposed to UV starlight, these radiative excitation processes actually compete very effectively with collisional processes, inelastic collisions. And as a result, in fact, this kind of behavior can be explained by a slab of gas that's approximately isothermal, a single kinetic temperature. In this case, maybe 50 or 60 Kelvin. And the flatter slope out here that still looks like a Boltzmann distribution is actually the result of the radiative excitation, and to some extent, the competition with the formation process of new molecules, which also tend to produce nascent molecules in excited vibration rotation states.
John,
yes?
Do you see any effects of ortho and para H2 in these models? Or?
Oh, that's an entire lecture or two. Yes.
Oh, they have plenty of time. All right. We can say
no, but there's lunch. They're going to get hungry.
All right.
Or I'm going to get hungry. The answer is yes. Yes. Also, I said in explaining, reminding you why there's no permanent dipole moment in H2. It's also a symmetric molecule, two identical nuclei. And so there is that additional symmetry property that enters the wave function, or spectroscopically, what we see is that there are two sort of semi-independent varieties of molecular hydrogen, because the nuclear spin alignments or anti-alignments associated with only one, uniquely with one or the other rotational wave functions to form a lattice. And so the para-form anti-aligned nuclear spins have only even values of the rotational quantum number, and conversely for the orthostates. And yes, we do see interesting effects, but in fact, it's been my contention that this is actually where an interesting reactive scattering process comes into play. That the cosmic ray ionization rates are rapid enough to keep small concentrations of free protons and H3 plus molecules in these neutral molecular clouds, as we've seen, and reactive collisions between protons or H3 plus and the H2 are a process that can interchange the nuclear spin species. And that, again, in these typical diffuse molecular cloud conditions, those spin exchange reactions are fast enough to compete with all of these other processes and effectively equilibrate the ortho and para hydrogen. So that in fact, I would maintain that for most of the observed cases, that is by now more than 100 diffuse clouds where the H2 has been observed directly, and the population distributions well measured, that in fact the apparent orthopara temperature, that is corresponding to the ratios of the J equals 1 and J equals 0 populations, are actually probably the closest thing to the kinetic temperature. Okay, so that, yes, the orthopara. I can be awfully long-winded, I'm sorry, but the answer is yes. The effects are important. We have to think about them and incorporate them into models, because that's the way that we can hope to get the maximum amount of information out of these observations. Okay, let me take you actually to a simpler example on the next slide here. These are some astronomical spectra that have been flattened and normalized, showing again interstellar absorption lines now in the far red part of the visible spectrum. The wavelengths close to 900 nanometers. These are absorption lines of interstellar diatomic carbon, C2. Another symmetric molecule, no dipole moment. However, the nuclear spins in this case are 0. So there's no distinction between any ortho and para states. It's just that all of the odd-numbered rotational quanta are absent. Astronomical spectra actually provide beautiful examples of spin effects in molecular physics. Diatomic carbon, at least the 12C nucleus, 0 nuclear spin, we see only half of the possible rotational quantum numbers present. If you look at a cometary spectrum that has both mass 12C2 and 12C13C, you can see all of the possible rotational quantum numbers in the isotopically substituted form. You actually see it directly in the spectrum. It's a beautiful demonstration of spin effects in spectroscopy. Anyway, back to this. So here we have another case where we see actually highly rotationally excited C2 molecules. And this actually was the original way that Avena van Dishoek and I decided to present the C2 excitation diagrams. They're inverted. Notice there's a minus sign here, so they look upside down compared with the other ones that you've seen. But it's the same idea. And here again, it looks as though there's more than one temperature component in the gas that produces these absorption lines. And again, the same thing happens, that there's a competition between radiative processes and collisional processes in establishing the rotational population distribution. This can be understood, and it's the result of taking into account, well, in 1982, these absorption and fluorescence processes and cascades through intersystem transitions and all kinds of stuff. It turns out we're doing an even better job of it with modern spectroscopic data now. The result is very, very, very similar. In any case, after taking all of that into account in models, we find that we assert that we can use these population diagrams to tell us not only something about the kinetic temperature by looking at the populations at the lowest levels that have the longest radiative lifetimes. And here again, this is quadrupole transitions only to relax, do the final relaxation of the rotational states. And this is C2 with an even smaller rotation constant, so the transition probabilities are exceedingly small, especially for the lowest transitions. But in any case, the populations in the lowest states give us an estimate of the kinetic temperature, and by matching models to the slopes on these excitation diagrams, we can also get, we can quantify the competition between collision rates and radiative rates. We know the radiative rates pretty well because in this case, the radiative effects are accomplished by red starlight, which we measure directly. And so we have a very good idea of what the average intensity of red starlight is in our part of the Milky Way. And it doesn't vary too much from place to place. Yes?
So, I'm not familiar with the excitation diagrams. What is being plotted? Is it the
Oh,
rate?
sorry, again. Yeah, I just skimmed over that because we've seen many of these in previous lectures.
Yeah.
But from the absorption spectrum, the strengths of the different absorption lines, in this case, they're very much unsaturated. So the amount of light absorbed in each one of these lines is proportional to the column density of the absorbing state. So we get the population distribution directly from the observations. That's the column density in each rotational level. And then plotted on the vertical axis is the logarithm of the column density and rotational level J divided by the statistical weight. Okay. And versus a linear scale of the excitation energy of the absorbing state above ground. So on a graph like that, for a Boltzmann distribution, you would have a straight line, and the slope of the curve, if it were a straight line, would be inversely proportional to the temperature, the Boltzmann temperature. Oh, well, I was just going to show one additional example of a symmetric molecule, C3, the next carbon chain, and we can observe C3 through optical absorption as well. This is now in the blue-violet part of the spectrum. And do the same sort of analysis. Again, the observations show this sort of characteristic 2 or 3 slopes, and again, we can use that to infer something about the temperature and the density. Okay. I want to remind you, again, the detailed notes are posted, and I'm only going to go through these slides very, very quickly. Remember last time I introduced the equation of radiative transfer, that is how the intensity changes with depth through an absorbing and or emitting medium. Right, and we can write down, a general solution for the emergent intensity in relation to any background intensity. This is the absorption term, the optical depth. We've transformed from linear depth through the absorbing column to dimensionless optical depth. And then for the emission contribution, we have an integral over something called the source function times the attenuation of radiation at exactly that frequency through the source medium itself. And the source function is the emission coefficient divided by the absorption coefficient. For simple spectrum lines, that has a very simple form. The source function can always be expressed as, in the simplest case, can always be expressed as a Planck function at some temperature, the excitation temperature that characterizes the ratio of the populations of the upper and lower states of the transition. And we start out with a set of abundances of the elements like what we observe in the sun. Okay, that gives us far too many parameters to vary for only 2 observed spectrum lines. But with those assumptions, we can constrain the range of total density of gas in the emitting region and the temperature. And it's fairly well constrained by the size of the source, the absence of corresponding hydrogen lines, and the brightness of the associated continuum. Because the continuum opacities and the continuum brightness is closely related to the emissivity in these Rydberg transitions in equilibrium. Okay, so we have several constraints from the observations. In addition, I think sort of for the first time, it's possible to make a direct connection between radio observations of a star itself and the visible spectrum. And it turns out that by much the same model, it's possible to account for several forbidden lines that appear in the visible and far red spectrum of the star, the high resolution visible spectrum. So Hussein certainly knows that Rydberg atoms are beautiful things. And just to leave you with the last slide to suggest a sense of beauty in nature, that these are actually slices and projections of probability distributions for the states of Rydberg molecules that are formed where by a multi-channel Rydberg atom, where the very, very distant electron creates a chemical bond with a rather distant ground state atom. And so these contours in the population density, when you take a slice through them, look like the fossils of ancient organisms called trilobites. So anyway, there's lots of beauty in nature, and you can find it even in graphs of wave functions, as well as all of these marvelous things that we see in space. So thank you for your attention.
When a hydrogen molecule is dissociating through this excitation and falling upon this intermediate what are the typical temperatures that these hydrogen atoms have?
Yeah, the dissociated hydrogen atoms. That's a very good question, actually. It's about, again, for the interstellar application, we try to account for all of the possible absorptions, the efficiencies of dissociation, and also weight the average by the wavelength dependence of the input star line. So that average value is about 3/4 of an electron volt per atom pair. So it's a little bit less than 1 electron volt of excess kinetic energy on average. Any individual channel, you can find some where it's a bit more and some where it's a bit less. But that's, on average, it's a little bit less than 1 eV per atom pair. But one electron volt is very large compared with the average thermal energy at 100 Kelvin for the kinetic motions of a few tens of millivolts. So that's a big energy input every time it happens. So that's one of the heating processes in diffuse molecular clouds. That excess kinetic energy eventually gets randomized through elastic collisions and joins the Maxwellian speed distribution of the molecules.
So in one of your slides, you show that the cascade or the Einstein coefficient. So how do you excite the H2 molecules?
Yes.
They tend to be -7.
That's correct.
Right. So
For vibrational
during
transitions.
the time when it's cascade, could it also happen to have other chemical reactions happening?
Yes, yes, chemical reactions or inelastic collisions that turn that excitation energy partly into kinetic energy. So, yeah, let's just do a simple order of magnitude calculation. The radiative rate 10 to the -7 per second, and for inelastic collisions, the collision rate coefficient might be, say, at most 10 to the -11 centimeters cubed seconds to the -1. So it's only at number densities of the order of 10 to the 4th molecules per cubic centimeter when the radiative cascade by these slow transitions might be interrupted by collisions. So that's the density of a dense molecular cloud, but it's still 100 times larger than the density of the diffuse molecular gas, where we actually observe the molecular hydrogen directly in the ultraviolet. So if the radiative cascade goes to completion in the diffuse molecular clouds, it would not in the outer parts of a dense molecular cloud. So it's a very good question. Yeah. Yes?
Could this, because I see now that this is around 6,000 K, 1 eV, could this hydrogen and thermal atoms dissociate larger carbonaceous molecules? Or is does this energy?
Yeah, that's actually a very interesting point. I think that I don't remember that has been considered in recent years. The first thing to be concerned about, it's enough. It's certainly enough energy, possibly, to do some damage to big molecules, for example, or something like that. And certainly enough energy to do some modification to isoson dust particles or something like this. So the energetic neutral atoms. The thing to consider is whether, again, is to look at the competition between the elastic collision rate with other hydrogen molecules that will thermalize the excess energy versus the inelastic collision rates or the collision rates with fragile molecules where the excess kinetic energy would cause a reaction or some structural damage to a dust particle or something. So, yeah, it's worth thinking about.
When light scatters through solid material, the index of refraction has an imaginary component which accounts for the absorption and a real component which amounts for the scattering out of the line of sight.
Mm-hmm.
Both of those need to be taken into account for observations.
Yeah.
You're talking here about single atoms or single molecules. Is there still, and so you've talked about the absorption cross-section, so that's the imaginary part of the index of refraction. Is there a corresponding real part?
Yeah, the scattering. Well, if you think about it, that's in the molecular case. Near the beginning of the talk, I showed. In the extreme line wings of an atomic or molecular absorption, that basically starts to represent the scattering component.
So that would be.
You only see it at that level.
Okay, so that would be considered the real part of the index of refraction.
Yeah, yeah. Now, the other thing that we have to take into account in these models, because it's orders of magnitude more important than that, is the scattering component of the extinction by dust particles. And that's an important part of the radiative transfer models, especially for how ultraviolet radiation penetrates through gas, because the albedo is thought to be fairly high, especially at the shortest wavelengths. So the scattering component is quite large.
Thanks.
And angle dependent. So it's easy to solve if it's a one-dimensional radiative transfer problem, but in 2 or 3 dimensions it's a nightmare.
Any more questions? Thank you, everyone, very much for joining and thanking all of the lecturers today. Right now is lunch.
And two, that we start out with a set of abundances of the elements like what we observe in the sun. Okay, that gives us far too many parameters to vary for only 2 observed spectrum lines. But with those assumptions, we can constrain the range of total density of gas in the emitting region and the temperature, and it's fairly well constrained by the size of the source, the absence of corresponding hydrogen lines, and the brightness of the associated continuum. Because the continuum opacities and the continuum brightness is closely related to the emissivity in these Rydberg transitions in equilibrium. Okay, so we have several constraints from the observations. In addition, I think sort of for the first time, it's possible to make a direct connection between radio observations of a star itself and the visible spectrum. And it turns out that by much the same model, it's possible to account for several forbidden lines that appear in the visible and far red spectrum of the star, high resolution visible spectrum. So Hussein certainly knows that Rydberg atoms are beautiful things. And just to leave you with the last slide to suggest a sense of beauty in nature, that these are actually slices and projections of probability distributions for the states of Rydberg molecules that are formed where by a multi-channel Rydberg atom, where the very, very distant electron creates a chemical bond with a rather distant ground state atom. And so these contours in the population density, when you take a slice through them, look like the fossils of ancient organisms called trilobites. So anyway, there's lots of beauty in nature, and you can find it even in graphs of wave functions, as well as all of these marvelous things that we see in space. So thank you for your attention.
When a hydrogen molecule is dissociating through this excitation and falling upon this intermediate what are the typical temperatures that these hydrogen atoms have?
Yeah, the dissociated hydrogen atoms. That's a very good question, actually. it's about, again, for the interstellar application, we try to account for all of the possible absorptions, the efficiencies of dissociation, and also weight the average by the wavelength dependence of the input star line. So that average value is about 3/4 of an electron volt per atom pair. So it's a little bit less than 1 electron volt of excess kinetic energy on average. You know, any individual channel, you can find some where it's a bit more and somewhere it's a bit less. But that's, on average, it's a little bit less than 1 eV per atom pair. But one electron volt is very large compared with the average thermal energy at 100 Kelvin for the kinetic motions of a few tens of millivolts. So that's a big energy input every time it happens. So that's one of the heating processes in diffuse molecular clouds. That excess kinetic energy eventually gets randomized through elastic collisions and joins the Maxwellian speed distribution of the molecules.
So in one of your slides, you show that the cascade or the Einstein coefficient of highly excited H2 molecules
Yes.
they tend to be -7.
That's correct.
Right. So
For vibrational
during
transition.
the time when it's cascade, could it also happen to have other chemical reactions happening?
Yes, chemical reactions or inelastic collisions that turn that excitation energy partly into kinetic energy. So, let's just do a simple order of magnitude calculation. The radiative rate 10⁻⁷ per second, and for inelastic collisions, the collision rate coefficient might be, say, at most 10⁻11 centimeters cubed seconds to the -1. So it's it's number densities of the order of 10 to the 4th molecules per cubic centimeter when the radiative cascade by these slow transitions might be interrupted by collisions. So that's the density of a dense molecular cloud, but it's still 100 times larger than the density of the diffuse molecular gas, where we actually observe the molecular hydrogen directly in the ultraviolet. So the radiative cascade goes to completion in the diffuse molecular clouds. It would not in the outer parts of a dense molecular cloud. So it's a very good question. Yeah. Yes?
Could this, because I see now that this is around 6,000 K, 1 eV, could this hydrogen and thermal atoms dissociate larger carbonation molecules? Or is does this energy?
Yeah, that's actually a very interesting point. I think that I don't remember that has been considered in recent years. The first thing to be concerned about, it's enough. It's certainly enough energy, possibly, to do some damage to big molecules, for example, or something like that. And certainly enough energy to do some modification to ices on dust particles or something like this. So the energetic neutral atoms. The thing to consider is whether, again, is to look at the competition between the elastic collision rate with other hydrogen molecules that will thermalize the excess energy versus the inelastic collision rates or the collision rates with fragile molecules, where that excess kinetic energy would cause a reaction or some structural damage to a dust particle or something. So, yeah, it's worth thinking about.
When light scatters through solid material, the index of refraction has an imaginary component which accounts for the absorption and a real component which amounts for the scattering out of the line of sight. Both of those need to be taken into account for observations.
Yeah.
You're talking here about single atoms or single molecules. Is there still, and so you've talked about the absorption cross-section, so that's the imaginary part of the index of refraction. Is there a corresponding real part?
Yeah, the scattering. Well, if you think about it, that's in the molecular case. Near the beginning of the talk, I showed, in the extreme line wings of an atomic or molecular absorption, that basically starts to represent the scattering component.
So that would
You only see it at that level.
Okay, so that would be considered the real part of the index of refraction.
Yeah, yeah. Now, the other thing that we have to take into account in these models, because it's orders of magnitude more important than that, is the scattering component of the extinction by dust particles. And that's an important part of the radiative transfer models, especially for how ultraviolet radiation penetrates through gas, because the albedo is thought to be fairly high, especially at the shortest wavelengths. So the scattering component is quite large.
Thanks.
And angle dependent. So it's easy to solve if it's a one-dimensional radiative transfer problem, but in 2 or 3 dimensions, it's a nightmare.